My name is Leliane, and I'm going to talk about symbolic font planning for temporarily extended goals. A work done with my PhD student, Viviane Bonadia dos Santos, and two of my former students, PhD students, Silvio do Lago and Maria Viviane Menezes. As you know, FONT stands for Fully Observable Non-Deterministic Planning. And in this type of problem, nature randomly selects a non-deterministic action outcome over a set of possibilities. We also consider the existence of dead-end states that may be avoided. Typical solutions for font planning are based on heuristic search with determinization, like PRP, which is considered the state-of-the-art on font, and symbolic model checking, for instance, the MBP planner and PACTL planner, which is a previous version of this work. In this paper, we claim that when solving a font planning problem, dead ends may be avoided if we plan for complex goal formulation. So if you know how to specify a complex goal for that domain, for that instance, you will be able to avoid dead ends. So, for instance, in the case of the NASA's Opportunity Mars rover, a goal specification that would work for him was move to a rock sample waypoint, avoiding dust storms. Consider phi a simple reachability goal that we are used with in deterministic planning. So I call that R goal. So a complex goal would be an extended reachability goal called XR goal that is given by two formulas. One for specifying the path goal and another the target goal. We call a generalized reachability goal, GR goal, also given by a pair, but the one that we can allow phi 1 to be true. So we can specify both types of complex goals with one formula. Also, we consider a complex goal a policy quality goal. So you can combine the other two complex goals with the quality of a policy being weak, strong, and strong cyclic. And planning for complex goals requires temporal reasoning and efficient solutions, as you know. So our approach uses symbolic reasoning, and the motivation for that it was because we observed that in deterministic planning, the first winners, planners, were based on heuristic search. And in 2014, as you know, the symbolic reasoning approach was on the top 5 best planners. So, and they were described in terms of preconditions and deterministic effects. On the other hand, the opposite happened in font planning. The most famous or the best planners from 2000 to 2012 was symbolic reasoning over state transition relations. That means the symbolic reason over the tuples state, action, and next state. And from 2012 to now, the state of the art is based on heuristic search and determinization. So it happens the opposite. So we could observe that there was no attempt so far to use symbolic reasoning about actions, but actions described in terms of preconditions and no deterministic effects. So our contributions are that based on the early works on planning as model checking, a temporal logic with the ramification or time ramification alpha CTL, we propose the first efficient symbolic font planner based on CTL, and that allows reasoning for complex goals and domains with dead ends and cycles. This planner also is competitive with the state-of-the-art solution based on heuristic search and determination, as we're going to show. So some font definitions are the basic ones, no? So I'm going to be fast here. So giving a font planner, I state given by a set of propositions, initial state, a goal formula that for our work, in our work, we're going to consider the generalized reachability goal and policy quality, a combination of these properties, and a set of states. We are going to encode states as a set of propositions, and that are true in that state, and the state transition takes from one state and an action to a set of possible states because of the non-determinism, and policies for informed are as usual, the mapping between states and actions, we consider deterministic policies. So solutions, as we know, informed can be of these three types of qualities because we consider that we have dead ends. We can have a strong policy, a strong cyclic policy, or a weak policy. The first one guarantees to reach the goal, never revisiting a state. The second one guarantees also to reach the goal, but possibly revisiting a state. And the third type is a weak policy that may fail when reaching a dead end, but for some outcomes it can be successful. So when we talk about an extended reachability goal, this type of policies also guarantees that some properties in the path are going to be to hold. So planning is model checking with also alpha CTL. What it is? This is our proposal is very strongly based on that language. So previous planners based on model checking using CTL did not implement the semantic of the logics, and our proposal of a font planner is totally based on the alpha CTL semantics. What is this? So alpha CTL has the same operators as CTL, no? Next, globally, finally, until, but has this dot in the middle of the operator. And usually in temporal logic, we express the semantic by the computational logical tree like that. Let's pick two operators. Exist, finally, phi, exist, phi1 until phi2. So the first express the reachability goal, and the second one express the extended reachability goal. But what we see here with alpha CTL is that you consider the actions. You see, the transition has actions, a label for the actions. So we read this formula as it exists a path from S through some action that finally phi is true. So there is an existential quantifier for actions in the semantics of the operators. I would like to compare both those two formulas, the same formulas, but one is alpha CTL formula and the right one is the CTL formula without the dot. So see that semantic is different. So complex goals with alpha CTL, now we can express them. They are now looks complex, but it's exactly the expressivity we wanted. So for weak policies, we want to say that given a domain and an initial state, I want that exists a path for some actions that phi1 is true until phi2 be true. And the most complex one is strong cyclic policy that I'm not gonna go through because we don't have time, but it's this formula. But for all globally exists phi1 until phi2. This is exactly the specification of the most complex goal we're going to work here. So it's a extended reachability goal for a strong cyclic policy. But how can we find policies that satisfies this formula? Well, we're going to use the basic two operations of pre-image. Weak pre-image, strong pre-image in alpha CTL. It's a little different from CTL because we now return sets of pairs state and action. So we really synthesize a policy while we do checking. So that's the difference between alpha CTL and CTL. This is the main algorithm, the pseudo code for the PA-CTL algorithm. And that's what we want to solve, the most complex formula for strong cyclic policy. So we need to have an algorithm for each type of policy. This is the most difficult. It's just to show that we only use the basic pre-image images over two functions. The one that computes the pair state action for the inner formula, and the one that computes the pairs, the resulting pairs, the policy, for the outer formula, for all globally, and exists until. That's really the translation of the semantics of alpha CTL. So I'm not gonna have time for this, but we can compute in this example the policy by applying that algorithm, right? Okay, that's PA-CTL, but now we want efficiency, so we need PA-CTL symbolic. How do we do that? So the first key point is, instead of computing the pre-image operation, we're going to compute the symbolic regression operation over the action description. So over the preconditions and non-deterministic effects. So we start by specifying actions in terms of preconditions and effects instead of the Kripke, the action labeled Kripke structure of alpha CTL. And now we have to write a formula. As a matter of fact, we are working with the QBF, so a propositional set of formula for a state, set of state, which is a disjunction of a conjunction of literals in the state, and a formula to specify preconditions and non-deterministic effects. We are going also to keep with each action description a list of propositions that change values by this changes predicate in QBF, which is a proposition, and finally we have all this formal description of the actions, and we can compute the regression with the basic operations that we already know in planning. So it's an abstract operation, because we have a set of states X, and we want to pick an action and compute all the previous states, regret this set to get all the states from which, if you apply action A, you end with this set of states X. This is done by this trivial formula, and this is not trivial, but this is QBF. I compute the same thing that I just told you with this formula using these two operations on symbolic model checking, which is restrict and exists. I don't have time to explain, but this is the translation for QBF. Now we can use this formula to compute alpha CTL, fixed point operations, in PA-CTL. And so this is just to illustrate that we can compute the set, the regression set Y, by performing these BDD operations. Okay, this is the symbolic efficient implementation of just this operation of preimage, weak and strong preimage, symbolic preimage. Okay, so the results are, we compare a PEC-TL scene with MBP and PRP on two domains. The first was a gripper domain, where a robot can drop a box supposed to carry a set of boxes to the elevator of a floor, and if he drops a box, the content breaks and he gets into a dead end. So we have two types of goals, a reachability goal and an extended reachability goal for this domain specified here. The first one is move all boxes to a target location. The second one is the extended temporal goal is carry each box with both grippers. It's a path goal formula until Phi2 be satisfied. Okay, so this is the results. In this domain, the PEC-TL was very efficient with very low times. We could not compare, of course, PRP and MBP on extended reachability goal, but even for reachability goal, the PEC-TL was very efficient because of this efficient symbolic reasoning. We also compared with the triangle, made a comparison in the triangle tire domain, and in here, I'm supposing everybody knows this domain, but in here, the PEC-TL sim were not good compared with PRP for reachability goal, simple reachability goal. But on the otherwise, look that for XR goal, the times were really good. That's because when you have a complex goal, an extended reachability goal, that takes into account the dead end, there is a balance between a good heuristic. We don't have heuristics, only PRP has heuristics. That there is a balance in terms of efficiency of solving a problem with a good specification of a complex goal that avoids the dead end, when compared with a heuristic search a planner that has good heuristics. So for this problem in special, heuristics are very good for estimating distances. So that's why we had these results. But we understood that this is a very good result when you compare with the solution with extended reachability goal. Okay, so the conclusions are that we have proposed the first symbolic efficient phone planner, PAZTL sim, that is a direct implementation of the semantics of the temporal formal logics alpha CTL, can solve complex temporal goals, such extended reachability goal for a strong cyclic policy. That's the thing that we encoded in the goal, is competitive in time with state-of-the-art solutions like PRP. And as future work, we need to do more experiments. And I'll tell you that I made available a non-symbolic reason prologue version of this algorithm for you to enjoy. So thank you very much.